In module 9, we're going to look at how can we take everything we've seen so far for a component and extend it for system reliability. So in the previous module, we've seen how can we compute the probabilities of failures for a component. So single elements that are considered as indivisible. So this is, for example, in a bridge such as this one beam would be considered as a component. But then what we want to look at here is what happened for a system. When we have the assembly of several of these components, in this case, we have a parallel system in a sense where we could consider that we need the failure of all of our beam in order to induce the failure of our bridge span here. So just as we add in terms of state of a component, which could be failure or survival, we have the same here. Our system can be in those two states, survival or failure. And we want to quantify what is going to be the probability of failure, but at the system level rather than at the component level. So the different classes of problem. First, we have the component. This is what we've studied since the beginning of the course. So we have here for two random variable involved in the limit state function defining the survival or failure of this component. So whatever is in blue here would be, for instance, my failure domain. So now I can have several components that are ensemble in a series system. So in a series system, you can see this as a chain where each link would be a component. So the failure of any of my link would lead to the failure of my chain. So this is what characterizes a serial system. So in that case, if we look at each of those lines as being the limit state surface of one of my component, the failure represents the union of the failure domain of any of the link of my chain. So in that case, we see the intersection as the blue area here. So whether it is my first link, my second link, or my third link that fails, the system will fail as a whole. So in that case, we can represent if each of those link or each of those component has its own limit state function, the limit state function globally for the system is the minimum value of the limit state function for each of my component, meaning that if any of them is lesser than 0, the whole system has a limit state function equal to a value lesser than 0. On the opposite side of the spectrum, we could have a parallel system. In such a case, it's the opposite. All the component in my system must fail in order for the system to fail. So we saw it before, the span of a bridge made of multiple beams. All beams must fail to lead to a failure. So in that case, if we look at the intersection of all my limit state function, that represents the blue domain here in the upper right corner, meaning that all my component must fail for my system to fail. And in this case, my system level limit state function is the maximum of my component level limit state function. So the max of G1 up to Gn. So if any of those is greater than 0, even if all the others are negative, I'm still at a survival of my system. And then in practice, we can have a combination of both. So we can have some of my components that are in parallel, and we can have some of them in series. So we have a mix and match of different components, some of them being in parallel, some of them being in series. So what we're going to do typically is that we're going to regroup everything that is in parallel by taking the max over what is in parallel. And then whatever is in series, we're going to take the min over subsets that could be regrouped together. So this combination of max for regrouping first whatever is in parallel and then taking the mean over these ensembles. And that's going to give me my limit state function for my system. So this is the basics we're going to use throughout this module to characterize system level failure probability. So the problem we're trying to address here is how can we formulate system reliability problem in order to estimate their failure probability. So this was the introduction. We're going to see at the specific nomenclature that we're going to use in system level failure probability estimation. We're going to see at how can we formulate the system level reliability problem? How can we estimate the probability of failure associated with them with an analytical form method? Then we're going to see how can we do the same with Monte-Carlo or sampling based method. So that brings us back here in a core module of how can we formulate reliability problem, in this case, system reliability problem. And that's going to reuse the concept we saw previously in previous module, notably what we've seen in module 6 using the form method and using module 4 using Monte-Carlo method. So nomenclature, what is a component? How can we express a system that is going to be in series, system in parallel, a combination of series and parallel for a system? And then how does this lead us to the new definition of what is a survival set or minimum cut set? So again, we saw that g of x1 is the limited function for one single component. This one must be, in order to be used, to be able to be use form methods or these analytical approximation methods to estimate or probability of failure, must be continuous and differentiable. So we're going to use now variable s, that describe state variable, that describe the state of our component. So if my state variable s is 0, it means I'm going to have failure. Okay, so my limit state function is lesser or equal to 0. If my state variable si is equal to 1, it means that my ith limit state function is positive, meaning my component is in the survival domain. Okay, so this is for now at the component level. Now we want to go the same thing, but for the system level. So I'm going to say that my state variable for my system level, 0, I have failure, 1, I have survival. Now we're going to see how can we express those state variable at a system level from their formulation at the component level. So now let's look at a system that would be in series, okay? So in that case, we're going to say, as we saw before, for something that looks like a chain, I'm going to take the minimum of any of my limit state function to express my system level limit state function. So in that case, my state variable SS would be the product of any of my state variable at a component level, meaning that, remember, 0 is going to be failure. So if any of them fail, it's going to lead to that product being 0, meaning my SS is going to be 0 as well. Okay, so by taking simply the product of the state variable at the component level, I'm going to be able to define the system level state variable by the product of the component level state variables. And this is equivalent to taking the min of all those state variable as well, because they can take only values either 0 or 1. Now let's do the same exercise, but not for a series system, for a parallel system. So in that case, in terms of limit state function, my system limit state function would be the max of all my component level limit state functions. So in that case, if we want to express this in terms of state variable, my system state variable would be 1 minus. Here I need to take the product of the complement of my state variable for all of my component. So 1 minus S1 times 1 minus S2 times 1 minus Sm. So what does it mean? When we're in a parallel system, so 1 describes the survival. So if 1 minus 1 is going to be 0, so if any of them survive, this term is going to be 0. So if this term is 0, everything within the brackets is 0. 1 minus 0 stays 1, is going to survive. So the only way where I'm going to have a failure, so being SS equals 0, is that if this S1 is 0, so 1 minus 0 is going to be 1, they're all going to be 1. So if they're all 1, then 1 minus 1 is going to be 0, it's going to be S6. Okay, so this is the way to express with state variable the state of my system in terms of failure or survival. And this is equivalent to taking the max of my state variable over my parallel component. So now, what can we do in a general system that would be made of both some components that are assembled in series, some in parallel? So what we're going to do is that we're going to regroup everything that is in parallel in my max, and then I'm going to take the min of all the subsets that are regrouped within the maxes. So for instance, if we look at my system here, so imagine that these would be bridges I would need to cross to reach from a point A to a point B. So in that case, there are multiple paths I could take. I could directly go through that point 4, or I could go through 1 and 2, or 1 and 3. These are the 3 possible paths I could take. But here, if we look at what we were going to later further describe as here cut sets. So the cut sets are, what are the link I could cut? that will lead to the failure of the system. So for instance, in this case, I would have 1 and 4. So if 1 and 4 cannot be crossed, I won't reach from A to B. And in the same way, if 2, 3, 4 are cut, I won't be able to reach from A to B. So these can be seen as what we're going to later further see as cut sets. So in that case, to describe my system failure, or my system state, I could say it's going to be 1 minus here, whatever I have in parallel for 1, 4. So 1 minus S1, 1 minus S4. And I have another set that is going to be in parallel, 2, 3, 4. So 1 minus S2, 1 minus S3, 1 minus S4. And if I develop all these terms, I'm going to get these, the min of S1, S4, no, the min of the max of S1, S4, max of S2, S3, S4. So these two are equivalent formulation. So now let's dig a little further in survival set. So C is going to be my survival set, okay, or cut set. So in this case, it's going to be the set of component for which the simultaneous failure will lead to the failure of my entire system. So this is a general definition of cut set or survival set, but we're more interested in the minimal cut sets. So minimal cut sets is the component that the sets that don't contain redundancy, okay? Component that survival or failure wouldn't change the survival of my system. And then we can have disjoint cut sets. These contain all the complements. So it's explicit set that contains all the information. Okay, we're going to clarify all these categories. So let's take back our example with this kind of crossing a bridge to reach from point A to point B. I could further represent this by an equivalent system where I would explicitly kind of double G4, saying that this is my first set of 1 and 4, and another one where I double the fourth one, so that we can see the second kind of assembly of component here. So my cut set C, what would it would be? They could be 1, 4. This is clear here. They could be 1, 2, 4. Okay. They could be also 1, 3, 4. Yes. And they could be 1, 2, 3, 4. So these three. And they could be 1, 2, 3, 4. So these are all of my possible cut sets. Then if we look at the minimal cut sets, those that are absolutely required to lead to the failure of the system. So the minimal cut sets are simply 1, 4, and 2, 3, 4. Okay? Because in this case, in 1, 2, 3, 4, I could remove some of the components. So in this case, I could remove 1 and still have the 2, 3, 4 that would lead to failure. So this one, 1, 2, 3, 4 is not a minimal cut set. And we could have also disjoint cut set in a case where we're going to have explicitly not only those that fail, but also explicitly the representation of those that survive. So 1, 4 fail and 2, 3 here survive. So it's basically the cuts that we have there where we add the complement of those failing as well. But in the context of system reliability, those that we're going to be really interested in are those minimal cut set, okay? The minimal set that would lead to the failure of our system. This is what we need to consider to express our failure probability. So the plan of the section for formulating our system reliability problem, we're going to dig a little deeper in the minimal cut set. We're going to see how that requires for the evaluation of the failure probability, the inclusion-exclusion rule that we saw in the module 1 when we review key probability concept. And we're going to see how can we estimate the failure probability of system for first independent component as an introductory example. So let's again consider the state variable for a component being 0 for the failure, 1 for the survival. So we can express this using minimal cut set as being the intersection of the limit state function being lesser than 0. Okay, so in a minimal cut set, all the element must fail. So I can express this minimal cut set as 1 minus the product of 1 minus SI. So remember, SI being 1 is survival. So if I want the failure, it's going to be 1 minus SI to get 0. So this represents a cut set, the failure of, no, sorry, the cut set, a failure of a cut set represents the failure of a system. Okay, so that's why here we have the intersection, because it represents it's all the element of a cut set fail, the system will fail. So now if we want to describe the state of a system using these cut set, we're going to say that as we said before, the state of a system is going to be the intersection over the element belonging to a cut set of their limit state function being less than 0, and the union over all the possible cut set I have in my system. So this is equivalent of taking the product over my cut sets. So the product of everything inside my cut set, which is going to be something that's going to be in parallel, and where A are my components. So the innermost bracket here is my component state variable. Then in B, I have something that is in parallel, everything that is within my cut set. And in C, I think the product is the union over the possible failure for my different cut sets. So this is the philosophy we're going to use in the definition of the failure probability over cut sets. So again, the same example we're going to take for the state variable for my system, the product over the different possible cut sets of the failure of everything that is within each of my cut sets. In that case, I have two different cut sets. We said it was 1, 4 and 2, 3, 4. So if we express this, it's going to be 1 minus the product of 1 minus S1, 1 minus S4. And this is my first cut set. My second cut set, this is the outermost product. 1 minus S2, 1 minus S3, 1 minus S4. This is my second cut set. And if we develop all these terms, we would get all of these. So if we would do the exercise of looking at each possible combination of survival and failure of my component, if we evaluate this function, that will tell me 0 or 1, whether the system fails or survives. So in general, if we want to use these cut sets representation in order to evaluate the probability of failure, we're going to need to evaluate the probability over the union over an ensemble of k cut sets. And if we want to evaluate the probability over a union, what we saw again in module 1 when we review probability theory, we need to use the inclusion-exclusion rule, because there can be intersection between the probability or between the sets defining the different cut sets. So for instance, here, if I have three sets represented in the Venn diagram, we can see that we can have interaction or intersection between E1 and E2. And if I just sum the probability over the cut sets, I will double some of these and I will triple some of these in the case where I have three events. So what we need to do is to compensate for these doubling, tripling, quadrupling of information by using this inclusion-exclusion rule. So first, when I want to compute the probability of the union for events being the failure of my cut sets, I need to sum the probability of occurrence of all of my cut sets. So in that case, it's going to be the sum of the probability, but I'm going to double and triple some information. So I need to sum the occurrence of any pairs. I need to add the triplets, remove the quadruplets, and I'm going to oscillate like this. Where, as we've saw before, when we do just the first term, we're going to have an upper bound on our probability. Then if we remove the pairs, we're going to have a lower bound, we're going to have an upper bound, and we're going to oscillate like until we have an asymptotic convergence to the theoretical value. So if we apply this to this simple example, we have a truss such as this one, and we want first to identify what is going to be the minimal cut set. So in that case, we can see that we have either the members 7, 9, 8, or 10. So we've got any of them, since this is a static system, isostatic system, sorry. Any of those four that would fail would lead to a failure of the system. Then, since we have those kind of full square here, if we cut any two members in that square center part here, that would lead to the failure. So these are enumerated in that minimal cut set there. Then if we define that the probability of failure of any of those individual components, so any individual member, is 1%, and we assume that the failure probability of each of those is independent, then we can define the system failure probability as the probability of the union of those minimal cut set. So these minimal cut sets are expressed there. So some of the cut sets contain a single member, some of the cut sets contain two members. So we need to use to evaluate this probability of failure the inclusion-exclusion rule. So in this, we're going to have the probability of the union of all the probability of the events representing each of the individual cut set. So the first term of that inclusion-exclusion rule is going to be to compute the probability of any of those events. Okay, so for all the events containing a single uh, failure for a single member, I'm going to have 1%. So I'm going to have 4 times 1%. Then I'm going to have all of these pairs of variables. So 5 plus 4 plus 3 plus 2 plus 1 times the probability of having 2 bars failing simultaneously. So if we assume that they are independent, the probability of having 2 bars failing simultaneously is going to be 1% times 1% times the number of terms where I have 2 bars failing simultaneously. So this is for my first term here is going to give me 0.04. Then I need to look at the probability of not those 2 bars failing. EIEJs is 2 sets. So for instance, 7 and 1, 2 failing simultaneously. Okay, so in that case, I need to look at all of the possible combination and permutation of 2 minimum cut sets failing simultaneously. And if we do this, we're going to have 6.6 times 10 to the minus 4. We see it's much smaller than the contribution of the first term. Then if we do the same thing, we are going to add now for 3 sets failing simultaneously. Say it's 7 fails, 2, 4 fails, and 8 fails. All of this simultaneously. So we're going to see now within the power of 10 to the minus 6. If we go to 4 by 4, we're virtually, we've reached 0. So in that case, we can see that the final terms, we're going to get 0.0408, whereas with only considering the first term with 415, we're not too far from it, okay? So we're going to quickly have a negligible impact from the higher term we're going to consider in our inclusion-exclusion rule. So now let's look at a special case where we have independent components. So the failure probability of system is going to be the probability that my state variable is equal to 0, or for a component, the probability that my state variable for the component level is equal to 0. So I can represent that probability that the probability of failure, being this state variable being 0, as 1 minus the expected value for my state variable. So if we consider that my state variable is itself a random variable that can take a value either of 0 or 1, the expected value of such a state variable can be described as 0 times the probability of 0 plus 1 times the probability of 1. So the first one is going to get 0. That's going to give me that the expected value of my state variable is the probability that state equal 1, meaning I have the survival of my either system or component. And I can use this to express the probability of failure of a system when it is expressed in series. That's going to give 1 minus the product of the expected value of Sy. So Sy, my state variable being in a survival state. So the expected value of survival, 1 minus to get the failure probability. So it's going to give 1 minus the product of 1 minus my failure probability for my component. That's going to give me my failure probability for my system. We can do the same thing for a parallel system. That's going to be 1 minus the expectation of 1 minus product of 1 minus Si. So I have 1 minus 1. That's going to cancel out. I'm going to have 1 minus, I'm going to have expectation of 1, the product of 1 minus Si. Si equal 1 for survival. 1 minus going to give failure. So it's going to simplify to the product of my probability of failure for components. It's going to give me the probability of failure for my system. In a general case, we can have in the innermost part whatever here is in parallel, and we can have here what is in series in the outsidemost case. So if we look at a very special case where we have the same failure probability for each of my component, the failure of the component is independent from component to component. What is going to be my failure probability for a system if it's assembled in series? That's going to be 1 minus the product of to the power k of 1 minus the probability of failure of my individual component. So that means that the probability of failure of the system is going to be much greater than the probability of failure of my component. Okay, this is in the case where I have a system, series system. If I have a parallel system, the probability of failure of my system is going to be the probability of failure of my component to the power k. So that's going to mean that my failure probability of my system is going to be much smaller than the probability of failure of my component. So this is expressed visually in those graphs. On the horizontal axis, what we have is the probability of failure of my component. So same thing in the top and bottom graph. The vertical axis is the failure probability of my system. So component failure probability, system failure probability on the vertical axis. And the difference between the top and the bottom graph, top graph is from 0 to 1 in a linear scale. The bottom graph is from an arbitrarily small number up till 1, but this is in log scale, okay, to be able to see what happened in that part here. So if we look at our reference, the reference is going to be the green line. So green line is we have n equal to 1 component. So in that case, we can see that it's a linear relationship for a single component between the component and the system failure probability. Now, if we look at 10, 10 component assembled in series, we see something like this. We see that if we're in series, then the failure probability in the system is going to be much greater than the green line, if we can say the component failure probability. If we go with, instead of 10, 100 component, we quickly saturate to 1, being the failure probability for the system. If we do look at the opposite, in red, we're in parallel. If I have 2 component, I quickly go to 0. If we have 5, we go to something that is negligibly small. Okay, so keep in mind, the ballpark idea is that whenever I'm going to have parallel component, I'm going to increase my system reliability. Whenever I have series component, I'm going to decrease my system reliability. So I'm going to, so series, I increase my probability of failure. Parallel, I decrease my probability of failure. So in general case, when I want to evaluate my probability of failure over a system, what I need to do is to evaluate the probability. I need to use the inclusion-exclusion rule, which is going to give me the sum of the probability of occurrence for all of my minimal cut sets minus the probability for the simultaneous occurrence of failure in minimal cut sets. And I have to go like this over all the possible combinations of terms. And here, the probability of failure for minimal cut sets is going to be evaluated using the classic form and swarm we saw in module section 8. Then for the failure probability of multiple cut set together, we can evaluate this, and this is what we're going to see in the next subsection, using the system form approximation. Okay, and this is what we're going to look at now. So how can we evaluate the failure of multiple multiple cut sets simultaneously using a series system, a parallel system, and how can we do this in general? And then we're going to apply this to an example of failure mechanism. So again, we have 3 cases: a series system, which is like a chain where each link the chain fail. Then we can have a second case where we have everything in parallel and a combination of both. And we're going to see how can we evaluate any of those type of configuration using a form method. Same thing we saw in module 6. So little recap. So using the form methods, what we're going to do is that we're going to linearize or limit state function defined in the standard normal space U. So G of U is going to be equal to a form like this, a linearized form, which is going to be G of U star, which is going to be equal to 0 because we're going to linearize on our design point, which is going to be where G of U equals 0, plus the gradient of my limit state function at the design point times U minus U star. If we develop the rightmost term here, we're going to get this formulation. And we saw if we compute the expected value and the standard deviation of these things, we're going to get the beta, which is the ratio of mean and standard deviation of G of U, being this term, which can be further simplified as alpha U star, where alpha is my negative gradient, normalized gradient vector, and U star is my design point. So, and my design point is the point that has the highest failure probability while being on the limit state surface. So my U star is going to be equal to beta times alpha hat, which is going to be the value U, such as the smallest distance from the origin while being on the limit state surface. And we saw in module 7 that we can rewrite this limit state function as being beta minus alpha U lesser or equal to 0. Or if I send that minus alpha U on the right hand side, beta lesser than alpha U. Okay, I remind you, we obtained that equivalent formulation by simply dividing that limit state function by the ratio of the norm of the gradient divided by the norm of the gradient. And just by reorganizing the term, we obtain that equivalent formulation. Now we're going to look at the first case. What happened? How can we use form to evaluate the failure probability over multiple components? That would be a series system. So in that case, imagine I have three different limit state functions. So my first one is here, second one is there, third one is there. And I assume these fail in series, meaning that I want the failure domain to be the intersection of my failure domain for my three limit state function, as represented kind of that blue domain here. So my probability of failure system would be the probability of failure for the union of the event g of xi. So the component level failure for being less or equal to 0 for my tree, in this case, component. So we're going to say this is the probability of the union for that g of xi being less than 0. We're going to bring that back in the standard normal space. That's going to be beta less or equal to alpha ui, where alpha ui, we're going to call this vi. Okay, we're going to combine these two in a single random variable vi. So it's probability of union of beta less or equal than vi. So what we're going to say is that we're going to use here the complement of this expression. So instead of saying the union over these failure domain that can be seen in blue here, we're going to express this. We know that the integral over the whole domain is 1. So 1 minus the probability of the intersection. Instead of being the union of everything in blue, we're going to say everything in blue is going to be 1 minus the intersection of what we have in white here. Okay, now to do this, we simply flip the order here. So it's going to be the intersection over v less or equal than beta to express everything that is in white. And the good thing here is that this has a simple closed form solution. This is going to be 1 minus the CDF in n dimension, in that case, n equal 3, of the vector beta, which is the value of beta for each of my component. And this is not going to be a standard, an independent standard normal CDF. Is going to be a correlated CDF, where the correlation matrix is going to be defined by the product of my alpha vector for each of my component. Okay, so let's see a little closer how does this work. So imagine to have two components defining a system that fail in series. So in that case, imagine that the two betas are the same. It's equal to 1 for each of my component, so that my probability of failure for each component is the same, is 0.16. So that represents that joint CDF for these two, considering that correlation. In that case, the correlation, if I have something like this, is going to be 0. And the correlation, I remind you, is the product of alpha times alpha transpose. I have my first alpha 1, alpha 2. The projection of 1 on the other is 0. Okay, so that gives me a failure probability for the system being 0.29. Okay, I have it here. This is my point there. So this is a case like this one where I have some of the failure probability for my second component, some of the failure probability for my first component, and an intersection, meaning here both components would fail simultaneously. So this is why my probability of failure of system is a little lower than the sum of the probability for each component. Then if I would have something more like this, so we see that now we have something that is greater than 0 in terms of correlation coefficient, because I have a bigger overlap between the two. Now my probability of failure would be 0.23 rather than 0.29. Okay, I would reduce my failure probability, get it closer to the component 1, because I have a bigger overlap in my failure domain. If we push that to the extreme, we bring that alpha alpha transpose to roughly 1 by making that our two components have an mostly overlapping failure domain, then my system failure probability is equal to 0.16. So you see that now that correlation coefficient makes a kind of square wedge in my joint CDF for expressing the probability failure using that SORM approximation. If we go to the other end of the spectrum, instead of being a fully shared failure domain, made fully disjoint failure domain, in that case, you see that my system failure has double what I had in terms of component, because there's almost no intersection between the failure probability of my components. So if this one failed, the other one doesn't. So basically, I've doubled the possibilities for failing, thus I've doubled the probability of occurrence. For the case where we want to do the same thing for a parallel system, we're going to do something similar. So we have, again, as an example, three possible limit state function. And now it's the opposite. Instead of being the union that dictates the failure of the system, is going to be the intersection. So it's not any of them that must fail, it's all of them simultaneously. So we're going to get the system level probability of failure as being the intersection over all of my limit state functions being lesser or equal to 0. So that represents the dark red domain here that is in the upper right corner. So then we could express this by replacing my limited function, bringing this in the standard normal space, beta I lesser or equal to alpha I ui. We're going to again replace alpha I ui by our v. And we're going to say here, instead of expressing this as beta lesser than vi, so beta lesser than vi is kind of the upper tail in our standard normal space. We can, in an equivalent way, represent the lower tail probability by flipping uh, vi lesser or equal than minus beta. So and if I express this, I'm going to be able to use the same formulation I used before, saying the probability of failure for a system that is in parallel is going to be the standard normal CDF that is correlated by my R alpha correlation matrix, evaluated for my vector minus beta. And that's going to give me the failure probability for the intersection of my domain, where again, beta is the beta for the individual component, and R alpha is going to be the correlation matrix obtained by the product of all of my negative gradient vector. Where here, one issue we have is that we have linearized each of the respective limit state function at their design point U star. But the design point U star might be good representation of the failure probability for the individual component, but might not be for the system as a whole, which occur here. Okay, so we need to take a closer look at how are we going to identify the failure point in the case of a system, uh, uh, a parallel system failure domain. So if we look at the current way we're finding the design point or the design point, we look at each of those design point individually. In a second case, what we could do if we want to improve this, we're going to take a single joint design point. That joint design point is going to be the one that makes the closest approximation of or joint failure domain for all of my components. The third option would be we're going to use a linearized design point. So we're going to take the linearization of our limit state surface, find the intersection that falls in the joint failure domain, and use that same design point for all of our components. In practice, if we use this, we're going to have a fairly rough estimation because our limit state function for the component are not going to be evaluated or linearized close to what is really leading to the failure of our system. If we use this, we're going to have a very good approximation, but however, finding that optimal design point is rather complex. Instead, what is going to be used in practice is that we're going to linearize the limit state function in cyan here, find the intersection that falls in the design point, and use that joint design point for all of my component. That's going to give me a new set of linearized limit state that are going to give me a fairly accurate representation of my system failure domain. And this is what would be used in practice to find a joint design point for all of my components. And if we want to generalize this for systems that are both some of them are in parallel, some of them are in series, we're going to use again our inclusion exclusion rule that we saw before, where the probability for the joint occurrence of different cut set is going to be estimated using the form method we just saw. Then we're going to use that inclusion exclusion rule over these ensemble of cut sets. The issue with that inclusion exclusion rule is that the number of terms we're going to need to evaluate grows really quickly with the number of minimal cut sets. But the things that plays in our favor is that the contribution of the probability of occurrence of things that contains more and more cut sets decrease exponentially as we increase number of terms we consider. Okay, so basically it means that we're going to have a very good approximation, typically even after considering only the first sum of the probability for the individual cut sets. So all the other events for pairs of cut sets, triplets of cut sets, they're going to have a really quickly decreasing contribution. So even if we don't consider all the calculation, we consider just a substance of them, we're going to get a fairly good approximation. And we can further improve this approximation if we want to use by these formula that will give us a little more accurate upper and lower bound if we want to truncate using only the first two terms. In this case, it's going to give us a little narrower upper and lower bound than simply doing our first two terms calculation in the inclusion-exclusion rule. So if we want to apply this to see really how it's working, we can look at an example involving failure mechanism. So in that case, we have a rigid frame where the moment capacity for this joint is M1, M2, M3, M4, and M5. And I have two forces applied, horizontal force H, vertical force V. The height of the frame is 5. That mid width is going to be 5 meters as well. So I'm going to have 7 total variable. My 5 resisting moment of my rigid joint that are going to be represented by a log normal random variable. They're going to be correlated with correlation of 0.3. The horizontal force is 50. It's going to be gamma. Sorry, the mean is 50. It's a log normal random variable. Vertical force is gamma. These two are independent of other variables. So I'm going to define 3 failure mechanisms. The first one is going to be a lateral flexion. Okay, so in that case, we can define our limit state function using the difference between internal and external virtual work. So in that case, the first limit state function is going to be M1, the capacity of my first plastic joint here, plus M2. M3 doesn't plastify, so I'm going to have plus M4 plus M5 minus 5H, okay, the force or work exerted by my horizontal force. The second one is going to be the plastification of my joint here. So M2, twice the rotation for M3, twice the rotation for M4. Oh no, plus M4, one the rotation, minus 5V. The third one is going to be M1. This one doesn't plastify, it's stiff. I'm going to have twice the rotation 2M3, twice the rotation 2M2, 2M4, sorry, and M5. And I'm going to have the combination of H and V, so meaning minus 5H and minus 5V. So if we want to consider the system reliability for these 3 possible failure mechanisms that may or may not occur simultaneously, we want to do a form analysis for any of them. Okay, so we use the same thing we saw in module 6. We do a form analysis. This is going to be beta 1, beta 2, beta 3, PF1, PF2, PF3. We see that the third one is the most likely, 0.023. Then it's going to be the mechanism 1, then it's going to be mechanism 2. Okay, and if we see that if we would sum the probability of failure of these 3 mechanisms, we would get something that's in excess of 0.03. Okay, but this is not what we want to do because there's some overlap in the possible occurrence of these failure mechanisms. And how do we handle this? Using a series problem. So either one can happen, or 2, or 3, or all of 3 simultaneously. So to handle or to compute that probability of failure, we need to compute our correlation matrix by taking the product of our alpha vector that were obtained from the form analysis. In that case, my system form probability of failure is going to be 1 minus that 3-dimensional CDF with correlation matrix R alpha and evaluate at the beta vector. Beta vector is the beta of my tree, 2.27, 2.88, 2. So in that case, it's going to give me a system beta of 1.9 or a probability of failure of 0.27. So remember, if we would just sum the 3 probability of failure, we'd get something that is greater than 0.3. Now we see that because of the possible overlap, we get to something that's smaller because we need to take into account a possible intersection in the occurrence of those different probability of or failure mechanisms. And now let's see how we can do the same thing with sampling instead of relying on our analytical form approximation. So we saw in module 4, when we saw Monte-Carlo sampling for estimating probability of failures, that the Monte-Carlo estimator is the expectation over the indicator function of my random variable x. So that means I'm going to take 1 over m, my number of samples of my indicator function, 1 being failure, 0 being survival. So my here indicator function could be 1 minus my system state. I'm going to get, using my formulation I said before, this. So basically where s of I, my state variable for my component, is 0 for failure, 1 for survival. Keep in mind, for my indicator function, the sign is flipped. So if we review the same problem we saw before for the failure mechanism, I'm going to get three different failure mechanism. I'm going to evaluate 0 for failure, 1 for survival at the state variable level, and I'm going to generate, in this case, 10 million samples. Okay, and I would get in my Monte Carlo sampling analysis 0.026 for my form 0.027. So we can see that we're fairly accurate using our form approximation compared to what our Monte Carlo analysis would leave us. So in summary, we can see that the reliability of a system can be analyzed as a series of minimal cut set that are basically component in parallel. So we can evaluate the probability of failure for ensembles of minimal cut sets using our form approximation methods that are very useful because they're going to be able to evaluate the probability of failure using a minimum number of evaluation of our limit state function. And then when we have a mix of components that are in parallel and in series, I can evaluate this using what I'm going to have with my form approximation in parallel to obtain the probability of failure of different cut sets. And I'm going to use the inclusion-exclusion rule to obtain the probability of failure of my entire system by taking the sum of the probability of failure of cut sets, taking one by one, then pairs, then triplets, etc. For my form approximation for system level, I'm going to be able to approximate that failure probability for a series system by 1 minus the standard and normal CDF of beta and with correlation matrix R alpha. That R alpha, I remind you, is the product of my alpha vector obtained from standard component level form analysis. I can do the same for a parallel system. Now it's going to have standard normal CDF of minus beta with the same correlation matrix. And when I have a general purpose system reliability, where I can have some part that are in parallel, some part that are in series, I'm going to represent everything that is in parallel using cut sets that are going to be obtained using that form approximation. And then I'm going to use inclusion-exclusion rule to calculate the union over these different failure over cut sets. If I want to do this with using Monte Carlo analysis, I can do the same. I just use standard Monte Carlo where my indicator function is going to be 1 minus my state variable for my system. And I can evaluate in the same way as I saw with the techniques we covered in module 4. So that finished what we wanted to see here with module 9, where we have extended everything we've seen so far for component to system. And the next thing we're going to look at is how can we take into account the both aleatory and epistemic uncertainty associated with the knowledge for the parameter of all the random variables that are involved in defining the, 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 the either resistance or solicitation involved in our limit state function.